Okay, these three graphs I asked you to draw up on your calculator to kind of take a look at them. The absolute value of x we looked at in class, that's the V shape. And we said that it didn't have a derivative at x equals 0 because that was a sharp corner. The slopes coming in on one direction were -1. The slopes coming in on the other direction were +1. So the limits didn't match up from the left and the right. Hence, there's no derivative at x equals 0. And if you take a look at x to the 1/3, the same thing's going to happen. If I come in here and I've got both of them on here graphed, but I'll just show you one at a time. And let me turn off the second graph here. All right, so if I graph x to the 1/3, notice I've got something that looks like the y equals x cubed function turned on its side, but here's the thing. At x equals 0, the slope goes vertical right there. So that's why this one doesn't have a derivative at x equals 0, because you have a vertical tangent line. And then x to the 2/3, if you graph that one, and let me turn this one off and turn this one on and take a look at the graph of it, you notice it looks a bit like the absolute value function, only it's got a little bit of a curve to it, but it has that sharp corner again. So on the first one and the third one, they don't have the derivative at 0 because of the sharp corner. So sharp corner. At x equals 0. Okay. So on the graph on example 5, they're asking, determine the domain of the function. Find the intervals of continuity and differentiability of the function. So for this one, let's take a look first at the domain. Going from left to right, we're looking for any x value that's not associated with a graph. So for example, as I go left to right, all of these x values line up with the graph except at x equals -2, and I have a vertical asymptote there. But then if I keep going, I'm still going to have graph x equals -1, x equals 0. Even at x equals 1, I have a solid dot up here. So x equals 1 is still in the domain. Keep on going to the right, and I have values of x on the graph. All the way over to x equals 4, and it appears like, well, there's no value there, but there is a solid dot up there. So there is a value function at x equals 4. So the only place that I don't have value of an x is at -2. So the domain of this goes from -∞ to -2, or -2 to infinity. If I'm looking at the interval where it's continuous, well, I can kind of pick out where it's not continuous by looking at the different discontinuity points. So at -2, and we'll just write this out, at x equals -2, you have an infinite discontinuity. Here we go. All right, so that's 1. We have another, so again, continuity means if I have to pick up my pencil and start again, that's where it's not continuous. So I'm good up until -2. I had to pick up my pencil and then come over here. And then here I have to pick up my pencil again and keep going. So at x equals 1, I have a jump discontinuity. You're going to need to know the different types of discontinuities. That's why we're going through this. And then we keep going. We don't have to pick up our pencil until I hit the number 4. And then I have that removable discontinuity. And then I can keep going to the right without having to pick up my pencil. So beyond 4, I'm cruising right along. So the function is continuous from negative infinity to negative 2. And then there's a definite break, and there is no value at negative 2, all the way over to coming in from the left side, 1, and there's a solid dot. And again, you're reading off the x-axis. Or pick it up on the right side, 1, 2, and then at 4, we have a parenthesis. And then 4 all the way out to infinity. Okay, so that's where we're looking at continuity. So where it's not continuous, it's also not differentiable. So I know it's those 3, but then there's other places where it's not differentiable, but it is still continuous. And those are the places that we're looking for our sharp corners, or we had our vertical tangent line, or we had a discontinuity. So these 3, like where is it not differentiable? Let's just look at the, can't spell and write at the same time, not differentiable. So where it's not continuous, it's not differentiable. So x equals negative 2, x equals 1, x equals 4. We're going to have issues there because it's not continuous. But then we also have issues at, so we took care of negative 2, negative 1. We've got an issue right here with a sharp corner. So at x equals 2, we have a sharp, we don't have to say sharp, but we have a corner point. Right, and then we said we got 4. And then right here at 6, we have a situation as well, and that's another like sharp corner. Right. So it is differentiable everywhere else except those values. So let's go from negative infinity to negative 2. Negative 2 to, what was our other point here? 1. And then 1 to 2. Two to 4. 4 to 6. And then 6 to infinity. Usually, though, we just ask where is it not differentiable. We don't usually give the intervals for where it is differentiable, but just simply looking at where it is not. And then being able to identify, well, it's not because of the corner points, or because it wasn't continuous at those points. Right. Higher order derivatives. Right. So if f is a differentiable function, then its derivative is also a function, and we denote that with the prime symbol. So f prime may have a derivative of its own, and we call that f double prime. That's what this is. It's the second derivative of f because it is the derivative of f. And we can use Leibniz notation to write the second derivative, d dx of dy dx. Sometimes you'll see it written like this, d, like d squared, or the second derivative of y with respect to the second derivative of x. Or, more commonly, we're just going to do the double prime that way. Right. So we'll do some, do we have an example? Maybe we don't have an example until we get towards our word problem. So we'll leave the blank pages for when we get back. And let's take a look here. So S generally represents position. So in this case, S is a position function for a moving object. V of t is the velocity function. Find and interpret S double prime. So here's the thing about this. S of t is t cubed minus t. The derivative of the position function is velocity. In other words, velocity is found by taking the limit as h approaches 0 of, and then we're going to take our, now let's just write it out, s of t plus h minus s of t divided by h. So the limit as h approaches 0 of, put the t plus h in, 4t cubed minus t plus h minus, and then s of t is t cubed minus t. Divided by h. Ooh, that's a hot mess. Because now you're going to have to take t plus h times t plus h times t plus h, subtract the t plus h, and then subtract the t cubed minus t, divide it by h, factor out the h, cancel the h's. Ultimately, what you would get would be 3t squared minus 1. That's why they're giving you the velocity, so you don't have to go through all that algebra. All right. The second derivative of position is the derivative of velocity. And the derivative of velocity is called acceleration. All right, so this, let's just kind of slump that down here a little bit, is equal to the limit as h approaches 0 of, now we're going to do into this formula. So this is going to be our v of t plus h minus v of t divided by h. All right, so v of t plus h, I go to the v function, I take out the t's, put in t plus h's. That's the first function, minus v of t all divided by h. So let's go ahead and compute that out. So we're going to do the 3 at the end, but we're going to take 3, and then t plus h squared is t squared plus 2th plus h squared. That's foiling this out. Minus 1. Distribute the negative. Then we're going to distribute the 3. So there's a lot of algebra going on here. Remember, everything in that second parenthesis should ultimately cancel out, and we should end up with terms that just have h's in them. So the plus 1 and the minus 1 are gone. The minus 3t squared and the plus 3t squared are gone. And so what you're left with are terms that have h's in them that you can factor out. So I'm going to factor out the h, and I'm left with 6t plus 3h, all divided by h. Cancel the h's, and then I can substitute in the 0 for h, which means this term's going to go, and I'm left with 6t. So the second derivative of position, which is known as acceleration, comes out to be 6t. And I think that is potentially the end of that section.